All right, hello everybody. Can you hear me okay? All right. Welcome. We're here to present StringSifter today. It's a tool for ranking strings according to their relevance for malware analysis. We're really excited to share it with you guys, to share it with the community. So yeah, I hope we can do that for you today. This is us. Our team from left to right is Michael Sikorsky. There is Philip Tully, our data science. And me and Jay Gibble were from the FireEye Labs Advanced Reverse Engineering Team, otherwise known as Flare. If any of you are familiar, the Flare On Challenge is going on right now, so you might have some familiarity. I'm not sure how it works with the con. Do we share the slides? Okay. We could probably put them on the GitHub, too. We'll share that at the end. Okay. So thanks. And also, this is a collaboration between the FireEye data science team and our reverse engineering Flare team. So, what's interesting about this string? At first glance, I could say that this probably indicates a sample uses the HTTP protocol because we see the word. Knowing a little bit about the protocol, I could say that this is a HTTP response header, so it might be capable of acting as an HTTP server. There you go. You nailed it. So the interesting part is the space at the end. And it's this little detail where we can see how much one string can have a significant impact on malware analysis and analyzing campaigns over time as well. So good observation. And this is, you'll see a strings output going by on the right as I go through this slide, just as an example of what you go through trying to analyze the strings output that leads to this particular string. So there's a HTTP web server called Nano HTTP that has this typo. It was released in 2012, and it's contained within this Cobalt Strike attack simulation tool. And you know, it's a tool for red teamers and also for malicious actors, as many of you probably know. And so that persisted until they patched it in January this year. So for about 7 years, this erroneous string was inside of the Cobalt Strike. So what can we do with that information? We can use that as a detection signature for intrusion detection systems. So we can detect malware across the network and on disk as well. But it goes a little beyond that, and that's what's cool about this particular string. This blog here linked at the bottom from foxit.com, they did some interesting research about tracking campaigns over time. Because all the publicly available, there's a set of data released by Rapid7 of just IP traffic. And you go through that traffic and find, you know, a campaign, how it evolves over time and how much people were using this server, and even get C2 addresses. So it's a pretty cool way to kind of track threat actors. Some of the traffic obviously is legitimate, and all kinds of interesting material you can gain just from one white space in one string. So running strings on binaries can produce upwards of 10,000 strings. And that produces a lot of noise, as you saw in that previous slide, mixed in with important information. So we want to try to solve this problem, how we can reduce the time an analyst has to spend sifting through the noise to get to this interesting information. So just take a quick step back, just to do a little review on how we define a string in this context. A string is a sequence of n characters followed by a null terminating byte. There's no context, there's no metadata to indicate where the string is, how long it is, what kind of string it is. Therefore, there's no context, and arbitrary data can be misinterpreted as a string. So anything within this sequence of printable characters on the ASCII table, if there's a sequence of however many, then that can be interpreted as a string. And this can be other things like, for example, x86 code. There are a lot of sequences of x86 instructions that will produce printable characters. And you don't know without any context whether that's an actual string or just a series of instructions. And that can also happen with memory addresses and resources, maybe an encryption key or an image or something like that. So there's a lot of noise mixed in that we have to try to sift these strings out. And then to further complicate, you know, Windows standard uses wide strings, which is the same as the ASCII, except different, a little more complex, generally just 2 characters with a double null terminating byte. So it's interesting to examine, how we have this asset of these strings. And as you look through the compilation process, we have this like simple C program that just prints the string Derby. And when it's compiled into this, compiled and assembled into this object file, that string has to exist. If the program has to use it somewhere, unless it's dynamically generated, it has to exist. So it's on the disk, and then eventually it's compiled into an executable, and somewhere in some section, there's certain conventions for where it would be, but could be anywhere in the binary, this string. So that's our asset as malware analysts, where we could take advantage of this process. And then our plan is to invert the process and work backwards, try to get from the string in the section back to what is the source code. So strings persist on disk, throughout the compilation process. And then we have this tool. This is the de facto tool for strings analysis. It's different implementations on different platforms, but it's generally called strings.exe. And it takes an input file or a stream of data and produces a output of all these printable character sequences. Here you have a little contrived example, but this is a kind of a sample of what you might see in a malware and the different types of noise that are mixed in with the fruitful strings. Up here you have, an artifact of the PE header. We have these C++ runtime strings. You have a user agent, which is a great network indicator. Some APIs, which might start to give us a indication of what the malware or the sample may be capable of doing. Some paths, file names, and even usage strings, which you'd be surprised how often you'll find things like this that tell you exactly what the sample's capable of. So just a quick little examination of our process with FireEye. When we have a customer who suspects a compromise, they'll likely, they see something suspicious in the system, they contact us, we dispatch our incident responders. They're going to do a forensic analysis on the system, perhaps identify malware samples or suspicious samples that may be malware. They'll perform a basic binary triage on the sample, and if they need further analysis, then they'll turn it over to the Flare team, and we'll do an advanced binary triage with full disassembly and try to identify all the capabilities of the malware, the extent of the hack, and things like that. And the end goal is to produce this report, which we can use to serve the customer. So along this process, every step of the way, strings can be utilized. The SOC analyst or whoever is working in the security department of the company might run strings to get an idea of what's going on. Our forensic analysis will involve running strings just to get an idea. And then when it gets to the reverse engineering level, that's one of the first tools in our kit that we're going to employ is running strings before we start our disassembly. And oftentimes you never even have to open IDA Pro. You can just figure out what it does from the strings. Run a quick Google, find the source code, analysis done, things like that. And these aren't the only kind of users we would have. Some examples on the bottom, red teamers for sure, and malware researchers. And there's lots of other people who are interested in ranking these strings and finding out the capabilities of malware by using strings. So knowing which strings are relevant requires experienced analysts. And as an analyst, the idea is to tell a story about the binary using the strings. So we want to order them, like you see here, in order of relevance. On the left, your left, you have things like runtime artifacts and library code that are going to produce a lot of this noise that isn't necessarily very useful. Then you have Windows APIs, which start to be a little more helpful, and it works its way up until you get stuff like source code you can Google through open source intelligence, user agent strings, which are network indicators, IP addresses, things like that. So we want to take that whole output and produce a story about what is this file capable of, this malware, is it malware, and what is the way we can serve the customer, the extent of the hack, what has been stolen, things like that. Of course, this relevance is subjective, and it requires experienced analysis, and even amongst analysts in the same capacity, it's just personal opinion on which is relevant and the exact ordering of these things. So that brings us to the goal that we're trying to achieve with StringSifter. The idea is to develop a tool that can identify and prioritize these strings and in order of relevance for malware analysis. And we want to do that in a way that's easy to use, that can generalize across all users, just with a simple, a couple keystrokes, and that inevitably the goal of all this is to save time in malware analysis. So how do we do this? I'm going to bring Phil up from our data science team to get into some of the more interesting technical details.
Sorry, 1 second. Maybe the battery died. I'll just go off the keyboard. So thanks, Matt. So I want to kind of get you guys in the mood of, hold on. Yeah, here we go. Of how to go about computing a rank of something. And ranks are everywhere. We encounter them throughout, in our daily lives extremely often. When we want to pick what stock we want to invest in, we look at the Fortune 500. We want to choose which college we want to send our kids to. We look at the U.S. best colleges rankings list. Decide what movie we want to watch. Alexa keeps track of how many of which domains are clicked most often on the web. We're all guilty of falling for this kind of clickbait. Ranks are fundamental, and they're interesting because they tell us something about how things are related to each other in an ordered fashion. Not only that, but our favorite products serve up rankings, unbeknownst to us, potentially. So every time you type a query into a search engine, that search engine is gonna stack rank a list of websites for you. That's gonna be based on things like your previous click history, users that are similar to you, what they've clicked before as well, what you've clicked in the past, etc. And this is kind of what keeps you going back to these search engines. Every time you log into a social network, typically your friends who are posting are not ordered chronologically on your timeline, right? They're ranked according to some relevance. So maybe your closer friends will appear higher up on your timeline, or people who you share common followers with will also kind of be shot up in that list. And then lastly, kind of recommender systems, the way that different websites serve up ads to us on like the side of news articles we read. Typically we see like 1 to 2 to 3 of those things, but generally for each kind of user on that website, you'll have a bunch of stacked ranked ads that are ready to go and be served up to that user. Anytime we choose a movie on Netflix or music on Spotify or something like this, they're always making recommendations to you. Here's a stacked ranked list of things that should interest you based on what you've listened to or watched previously. And so how do we kind of formulate this more systematically? And in machine learning, this is kind of referred to as the learning to rank paradigm. So the goal here is to take a list of input items, like you see on the left, and create an optimal ordering or optimal permutation of those list of items. And so, you have a list of 5 items here, and you apply some function to those items, and what you get is an ordered list of those items. And so the interesting part here is that the precise score of each individual item doesn't matter as much as the relative ordering, right? So I don't care that how much that white box is ranked above that red box, only that it is ranked above the red box, right? So precise scores are a little bit, we don't care as much about that. And so the objective here is fundamentally different than some of your more classic, especially when you think about like information security, the way that we think about tasks like classification, where you're trying to predict something like, is this email ham or is it spam, or regression or clustering. Each of these kind of tasks means that you're assigning a score or a label to one specific item. Here our task is fundamentally different. And from what I've seen, at least in literature and in various talks, this kind of notion is rarely applied in security applications. And so to make this a little bit more defined here, just like Matt said, we have a series of input files, and we want to run strings over each of those input files and generate a set of training data, right? And so our training data here is a set of strings outputs, can be as many as we want, and each of those strings outputs is going to produce a different number of strings within their output. And we're going to associate a label with each of those strings. That's going to encode its relative relevance within that list. So things like Matt said, like those PE artifacts, this program is running in DOS mode, is going to have a lower relevance because it's encoded by 0 versus something like a HTTP header. It's going to have a much higher relevance. It's going to have a higher label associated with it. And so again, this is kind of our objective now. We want to rank and create a permutation of these items within each individual strings output in order to push up the most relevant ones to the top and therefore make our analyst's life just a lot easier. How do we do this? The underlying algorithm that we're going to use is called gradient boosted decision trees. And so fundamentally, these are built by individual weak learners or decision trees. And so a lot of people already probably know what this is, but you essentially build up the tree by choosing splits based on this notion of Gini impurity. So each split might consist of some feature. So, whether or not a string contains the letters HTTP, that might be a split in the tree. And, when you split it, it's going to optimize this Gini impurity notion, and you're going to kind of combine these set of features and build out these trees up to a certain level of complexity. So gradient boosted decision trees take that notion of a single decision tree and combine many of them and kind of produce several of them. And it's going to iterate across several of them. And each time it adds a new tree, it's going to try to reduce some loss. And this process is called gradient descent because we already know the answers. We already know what our labels are, our ranking scores are. And the ensemble here is going to produce a weighted sum of all of these trees, and that's going to kind of help us generalize better. And this process is called boosting. The specific algorithm we're going to use is called LightGBM, which is based on histogram bins. But the point here is that we're not using a classification objective function, we're using a learning to rank objective function. So the point here is that we want to optimize the relative ordering of the items within this list. What training data are we using? We're relying on an open benchmark dataset that was released by Endgame called Ember. And so this dataset consists of 1.1 million PE files. 400,000 of them are malicious, and they split it up into testing and training, but we kind of just take all the malicious ones, which they have an easy criteria for judging malware of any file that has more than 40 VirusTotal vendors calling it malware, right? So this is kind of a safe set of malware for us. So we take all of those 400,000 malware samples and we run strings over all of them. And we produce something like over 3 billion individual strings from those files. But we don't need to necessarily train on all of that data, so we perform some sampling and we whittle it down to something like 500 million strings. And this is our training data set. And now we produce our ground truth by performing some heuristics, right? So the guys down there who are colleagues of mine and also Mike and a lot of the Flare reverse engineers have a lot of insights into how these things should be ranked. And so we go through a process of heuristically weighting them using weak supervision, and we can produce a set of labels for us from which to now predict from unseen strings outputs. So the next important thing we want to talk about, because we have our learning algorithm down now, we have our labels down now, and so we need to come up with a way to take those raw strings and convert them into something that the algorithm can understand. And this is called featurization. We produce hand-tuned features here, and we produce about a set of 80 different features, and we also use TF-IDF n-grams, so that set is much larger, in fact. But a few of the interesting ones that we wanted to point out to you include natural language processing features. So, one of the problems that Matt identified before was that a bunch of these strings within these outputs look completely irrelevant because they look like, a jumbled up bunch of mess that are not human interpretable. They might be x86 code or whatever they may be, just artifacts that we don't care about. We want to shove them down to the bottom. So how do we do that? One way in which we can do that is using a Markov model. And so we can take a known set of relevant strings and train a Markov model over that and produce a set of transition probabilities between characters within all of those strings, right? So here, you can imagine this as like a matrix, a 2D matrix where you have characters along the top and characters along the bottom. It's all to all, so you can have self-connections as well. But once you train this model, you basically say that the probability of a capital F being followed by a lowercase t within this data set is 0.07 versus the probability of a lowercase t being followed by itself, that self connection, is 0.14. And so in this contrived example, the t's might be more interesting if they're followed by themselves because you have things like HTTP that are relevant within these strings, and you can build this out. Once you build that out, you can apply it to unseen data, and you can, in a data-driven way, come up with a threshold that hopefully will nicely separate your noisy crap strings that you don't care about from your more interesting strings. And so that's one way. So this is what this looks like on a set of malware. I'm not sure if you can see this, but what you're seeing is a histogram here of average transition probabilities across entire strings. And so the further you get to the left, that's a lower score. And you see all that junk on the left-hand side. So this is kind of a nice indication that this might help us filter out that junk and score it lower. And then as you get to the right more, this is like a higher average transition probability. You see, we start to get things that look more like actual words. And so this could be a helpful feature for us. And so this is like a memory-based model. There's another model that we can come up with that's based on entropy, and this is memoryless. And so here we're just trying to compute the actual randomness of the string using Shannon entropy, and this is like a very classic technique. And so if you do the same thing, you take a histogram of that and you plot that across a bunch of strings outputs as input. You see the ones that have lower entropy tend to be a lot more regular. Right, so there are lots of repeating characters there versus strings that have higher entropy, and that's really small for you, but this is basically an enumeration of all the characters in that alphabet. So it almost represents like complete chaos or complete randomness from the point of view of this feature. And so for this one, what we want to do is filter out both the bottom junk and the top junk. So there's like a sweet spot in the middle there, and that's where we want to kind of capture that important information and hopefully filter out those meaningless strings. Lastly, and I thought this was interesting because there's actually a Scrabble game up here, so that's a sign. But we want to produce some more randomness measures, and we can use Scrabble scores. Everyone's played Scrabble. You can take a string and compute for each character in that string what's its corresponding Scrabble tile, what score that is, and just add them up and divide by the length of the string. Voila, you have a normalized Scrabble score. And this produces something like this, where you have strings with characters that occur very commonly on the left-hand side, and strings with very rare characters on the right-hand side. So lots of Z's, lots of Q's on the right-hand side, and those are also indicators of garbage. We don't really care about those. So we have another kind of sweet spot in this space, right? Obviously next we have other interesting malware-based indicators like host and network indicators, and we can also come up with regexes that capture things like format specifiers and base64 encodings and user agents, which are things that you would think also should provide the analyst with some important information. Just a side note about the Scrabble stuff. If anyone's an avid player, Quixitry was the highest scoring Scrabble word ever used in a professional match. The person who played this scored 365 points with this single word. Now, of course, in Scrabble, you have tiles on the board that have things like double word score, triple word score. We didn't account for those in our feature. But I thought the definition here was interesting. It's a noun that means behavior inspired by idealistic beliefs without regard to reality. And in kind of the days leading up to this talk, I was able to relate to this a lot. So let's kind of put these things together, right? We have labels, we have features that we take from input strings, and we have an algorithm to perform our ranking for us. So let's try to feed this a set of unseen input strings. Here is a very simple example. It's a strings output from a malware binary that produces 44 strings. And we feed this through StringSifter, and we get back something that should be more useful. I mean, this is not very many strings, so you can probably do this yourself a little bit easier, but you can imagine if there were thousands or tens of thousands of these strings, that this tool could actually end up being super useful for you, because you get things like domain names and file file names and other network-based indicators towards the top. And then towards the bottom, you get, PE artifacts, you get common DLLs, and you get a lot of this junk that we're successfully filtering out based on some of those NLP features that we invented there. So that's great. Looks like it works pretty well for that one sample, but I want to be able to kind of create more evidence for myself that this works in a generalized sense. So I want to be able to measure the performance of this across a host of different input strings, not just that single input strings output. And so here's the way in which we do this, right? So like I've described before, you have a query, which is a single strings output from a malware binary. And you have a trained model, gradient boosted decision tree. And so you can take that query and make a prediction using that model, and that will produce a set of scores. And so for each of the strings in that output, you have a score that becomes associated with that. And then kind of like the final step here is that you just have to sort that output according to those scores. Right? Okay, great. So now we have we have a set of output strings that we already know what their ranks should be because we have their labels, and we want to come up with some metric that we can use to convince ourselves that this should generalize across strings that the algorithm hasn't been exposed to before during training. And in the recommendation systems literature and in collaborative filtering literature, this is typically used. This is called the normalized discounted cumulative gain. It sounds complicated. It's not. I'll describe it in a second. But importantly, this kind of metric is very different than what you might expect from false positive rate or accuracy, other typical accuracy metrics you might expect from like classification or clustering algorithms. And so the first portion of this, I'll start with the gain. It's the easiest. It's just the magnitude of each string's relevance. So that's exactly what those scores correspond to, associated with those strings. You don't care about one individual score. You care about the cumulative effect of all of these individual strings. So you want to add them up. But before you add them up, you want to apply some discount. And this discounted gain ends up enabling you to care more about the strings that are ranked more towards the top of that list, because those end up being what you end up caring about a lot more. So when you kind of convolve this with some monotonically increasing function, like a logarithm, that does the job for you of kind of overemphasizing the ones that end up being ranked higher than the rest. And then finally, we want to normalize this because different strings outputs will contain different numbers of strings. So in order to kind of have a good comparison of our algorithm across different strings outputs, you need to kind of divide this by what would be the ideal discounted cumulative gain for that strings output. And this enables you to kind of compare across different algorithms that you might come up with or different parameters for these different algorithms. And it just kind of allows you to tune things and make things a lot tighter. So this, again, the whole point of this is to kind of make sure that we can convince ourselves that this approach can generalize across unseen samples, right? And what does this look like for a set of test strings that the algorithm hasn't been exposed to before? I have two kernel density estimate plots here. One is the gray one on the left-hand side. This is when I compute this normalized discounted cumulative gain score over strings outputs that haven't been run through our StringSifter algorithm. It's just the raw strings output. This is kind of expectedly bad, right? This is unsorted, unranked. This is exactly kind of the problem we're trying to fix with our algorithm and our approach. And then when we run StringSifter over these set of strings from kind of over 7 years of the malware reports that these guys are generating, you see that distribution, this NDCG distribution, shift over to the right-hand side. It's closer to 1. Higher score is better, and it's normalized, so it's bounded between 0 and 1. So you see we have some improvement here, quantitative improvement, and this is a good sign. So to kind of put it all together, before I hand it off to Jay for a tool demo, we have a set of input files that we train on some, and we test on some others. And we run them all through strings, right? So we produce a ton of different strings from these malware binaries. And we have training data where we know the labels. We have an input query, which is something like a strings output that the algorithm has not been trained on. And so we have our training data that we use to build our model with. And then we take the query and make predictions from that trained model. And finally, you have our prediction. And so after a sorting step with those scores, you can get back this kind of stacked ranked list of strings. And the goal here again is to kind of make the malware analyst's life much easier. And so I'll hand it off to Jay.
Okay, so a quick recap of what you've seen so far. First, you saw Matt from our reverse engineering team. He talked to you about strings and the power of strings, which among this community is probably somewhat mundane tool. It's been around forever, but it's powerful. It can be used for effective binary triage to guide further analysis of your malware sample. Then Phil came up and dropped knowledge bombs of data science for you. He showed you fancy tree plots. He talked about entropy. He talked about Scrabble scores. So the third component of this is what we really hope is the takeaway for you for today's talk, which is we are open sourcing this thing. We put it online live just this morning. It's on GitHub. It's on PyPy. If you guys have your laptop, if you have a Linux-enabled phone, you can pip install it and get running with it, before we're done this talk here. It's there now. Can you hear? Okay, so here it is, GitHub, FireEye, StringSifter. As a tangent, visit the GitHub FireEye collection of repos. There's a large number of things there, and there's some real gold in the FireEye repos. But hopefully we added one more nugget today with this StringSifter. This is also on PyPy, so you can do a pip install StringSifter. It contains some command line tools. It contains a Docker image that you can build, and we'll talk through all those things as we go. So once you install this, it gives you two primary scripts that you'll use. There's a tool called flare strings. There's a tool called rank strings, and the way you use it, very straightforward. Flare strings extracts the strings, you pipe it into rank strings, and you'll get the ranked result that Philip described. So this thing is versatile. The way the piping mechanism is set up, you can use other string generators. FireEye has an excellent tool called Floss that will extract not only the raw strings from a binary, but will also do code analysis and will extract, say, strings that are built on the stack or strings that are decrypted at runtime. So a lot of those like indirectly present strings within a binary are exposed by Floss. You can use that to pipe into the string ranker. You could also take a live memory dump, say an image of a PE file is collected at runtime. You can pipe that through the strings and extract the real value here. And when we talked so far, we've talked a lot about signal and noise, and the power of this tool is to take the strings output, which generates a lot of both. You get the little nuggets of information, and you get a lot of garbage in there, and this tool will float the nuggets all into one place so you can see them. Okay, so here's a quick demo of the tools. Here's how you install it and use it. We have a couple variations on this. This first one is the mode that I like to use. This uses Git, where you git clone repository onto your local machine. I keep it like an SRC directory or something like that, so you can see it lays bare the content of the repo, and you can go in there, you can look at the Python, you can look at the data files, it's all sitting there, and then you can use pip install with a -e flag. It does that's called an editable install that will run the setup program. It brings those scripts into your local working environment, but you can see and alter the code right there in place. So the instructions for that are on the right side. You can see it's just a few. If you're maximally lazy, this is the way to get up and running. Pip install StringSifter, one word, all lowercase, and once you do that, it's ready to go. Then you can run flare strings and rank strings immediately. The other one, the first one, is my preferred method because the source code, it enables easier visibility of the source code. When you do pip install, pip likes to store things in a deeply nested directory, or if you're running Anaconda or something like that, it'll be 15 levels deep, and it's very, very hard to actually find the good stuff. Finally, if you like to keep things contained in an isolated way, you can build a little Docker image and run it from within there. That'll install all the dependencies within the Docker container. Okay, we have a tool called Flare Strings. All of you have strings running on your computer, but we brewed our own special version, and I'll give the motivation for that in a moment. I do want to call out again the Flare team. It's FireEye Labs Advanced Reverse Engineering team. Matt is on the team. I'm on the team. We do reverse engineering in the what I would consider the hardcore sense. We disassemble, we debug, we unpack. If you have a PCAP, we'll parse it. If you have something that's obfuscated, we'll deobfuscate it. That's really something we like to do. And so this tool is it's planned for use as a preliminary reconnaissance tool that we can use to guide the further deep dive analysis. So there are many versions of strings. Strings is a classic tool. It's been around forever, and because of that, there's many different versions of it. So GNU, if you're a Linux user, you're accustomed to the bin-utils versions of strings. If you run on Mac, you have some fork of the BSD version of strings. If you're on Windows, heaven knows what you're running, but there's lots of different versions of that. So they all have their own set of features. So just to resolve that different feature sets, we have a simple tool in here called Flare Strings. And it's pure Python, and so if you run on any of these environments, Linux, Mac, Windows, you should get the same output. Just a side note, it prints both the ASCII and the wide strings. If you run the Linux strings, you have to run it twice to get both all the strings. And especially for Windows executables, the wide strings really have signal-to-noise ratio. They have much higher signal density, so you definitely want to not miss those. Okay, so here's a demo. Let's see if it runs. Oh, there it goes. Okay, so I started with a sample file. This is just called narrow and wide, and what you see here is a hex dump. If you look closely, you'll see there's some narrow strings, some ASCII strings, and there's some wide strings that have the zeros interleaved with the actual characters. So if you run the vanilla Linux strings on that, you only see the narrow strings. But if you run strings again with the -EL that reveals the wide strings, you only see the wide strings. And then if you run this tool, Flare Strings, you get them all. So the takeaway here is Flare Strings just gives you a more uniform, more complete output. Okay, then I'll show you a demo of this rank strings, which is really the core StringSifter program. Before we start, two things to know. One is that among our feature set, Philip mentioned as a kind of a side throwaway, but we have a large feature set, and one of them is we have collections of Windows API that have been identified. Windows API that are consistent with malware activity are segregated from other Windows API that are just kind of vanilla and we don't care much about. So in a desirable ranked strings output, you would see those show up in two like clusters in the hierarchical view. You would see the ones that are more associated with malware activity float toward the top relative to your innocuous Windows API. So what this demo does first is this is the classical malware analyst way of running strings. So this is not the rank strings. This is where we're computing the strings on a sample and piping it to less and just like eyeballing it. And so this is unranked strings. And what you see here, I'm paging through this using the less program. This is like a real malware analyst workflow. And you just have to hunt through all this stuff and look for good things. You may miss some things, but you end up spending a lot of time looking at this crap here. Anybody familiar with this workflow? Oh, look, there's some stuff. And so I back up a little bit. I see some API keys. It's kind of hard to read on this, but you guys all know what the strings output looks like. I see a registry key. Somewhere in here, there's a PDB path. This malware is the Zeus remote access Trojan. I compiled it from source. So yeah, there is a PDB associated with where I built it from. So eventually I either get to the bottom or just give up. And I'm sure all of you, if you have a large binary, like this can be prolific, and you can spend some time iterating with the width of the strings that are output by your strings program, but really this can be a headachy. Okay, so here, this is a ranked strings version here, and the takeaway for you is the density of the value of the strings that are in this set float up to the top. So if you imagine relevance score versus where the string is placed in the file, it's like a descending slope. You know, the juicy ones are up near the top, as if somebody raked all of the nuggets into one corner of the room, and you just go to that corner, and you can immediately address the things that are of interest. As a side note, since the feature vector that is extracted from the strings is going to be consistent with the string input itself, if you have a duplicate string, they'll show up ranked as a tie. So they show up together. In this example, we have this little program cannot be run in DOS mode. There's two instances of that because this one is a file that contains another file, and the contained file is not obfuscated in any way. So you just get the naked preamble there, and so you see it. They're co-located in this ranked strings output. So I encourage you, do the pip install, download this to your computer, run it against your favorite malware samples. This is primarily tuned for PE files. In future work, we're going to be working on Mac files and Linux ELF files, but I think a very powerful tool. As a good Python program, this uses argparse, and we have some options that you can use. I'll just, rather than talk through these, I'll just give you a quick demo. If you use this ---- scores, which is alias to -s, it'll just give you the little numeric score associated with the features, so you can see how hot the information is. So if you have a sample like this one is a sample of Dharma malware. It's a ransomware sample, but it's obfuscated. So there's only 2 visible imported API. There's no user strings in here. It's 99% this garbage. So if you look at the score on the left, we're looking at negative scoring stuff here. So this is just noise. So you can print, when I mentioned the descending slope of the information value of each of those strings, this actually shows you that slope. Then running again with the same sample, this min score option just says, you as the user can say, you know what, I don't even care about the things with score less than something. So in this case, I used score 4 because that's where the noise cutoff was on this particular sample, and it just gives me those 4 lines that were at the top. Okay, so we have this tool. It's stable enough and useful enough that we think it's ready for sharing with the community, and so we did. That's why we're here today. But we do plan to take this further as we continue to develop it. We would like to leverage the feature set that comes out of the derived features from the string. We can use those if we take that whole matrix of strings and feature vector and transpose it so that we're looking at the feature vectors and what strings correspond with those. We can use that as a potential screening tool for malware capabilities. Note that I say screening tool, not a detection tool. We really can't detect until we do a proper reverse engineering and code flow and say, is this thing really hit? Is this thing really used where we think it is? But in terms of preliminary analysis, this would be a valuable first step and time saver. We can detect and handle packed or obfuscated binaries. That Dharma example I just gave you, quite an example. Like if you took the rank strings output and did analysis on that curve, it's quite obvious. There's not. If you get a very low signal to noise ratio on average, we could use that as a tip off for further analysis. If we have a dedicated standalone unpacker, or if we need manual analysis to deobfuscate, that's a signal for that. Yeah, we can leverage the feature vectors to focus triage. Philip dropped a couple great techniques for natural language processing, but that is a huge area where if we view strings as a communication between the software developer who's writing code and writing messages and us as the people that are kind of looking at those messages, the space for language processing is just immense. And then, as I mentioned before, we do definitely want to extend this to other binary platforms, or Mako and ELF. Okay, so for community, it's here. Plug it into your malware analysis stack. Look at the red arrow. We are looking for critical feedback. We expect you to use this. You may like it. You may be annoyed by it. You may find features of it. It says, there's feature X that's in my sample and it wasn't illuminated by this, or it did a great job with this. Like, we want to hear that stuff. And so we have on our GitHub site, the issues is active and enabled. The last time I looked, which is about an hour ago, there was 0 on there. So be the first one to post an issue to our GitHub. But we want this to not be a one-way, here, take this tool and use it. We want this to be a dialogue so that we can improve the tool, so that it makes us better at FireEye, but so it makes you guys better too at your own malware analysis techniques. Okay, so thank you. We have a couple minutes. The guys are still here, so if any questions are there. Okay, excellent questions. The first question was, we have special handling for this program can only be run in DOS mode. If there's a typo in that or some deviation from that, would it have been pushed down like it was, or pushed up?
Yeah, it's a great question. So that specific string is part of like a little bit of a whitelist that we have, right, as a feature. But we also have other features like these randomness scores, right? And so we have features that detect when input strings look more like the English language. And so because that string, it's not exactly hitting that whitelisted strings output, it should be detected as something that looks more like English, right? Because it is. It has that exclamation point, but generally, looks like English text. And so I'm not sure off the top of my head what the score would be, but I would hope that we could cover that individual feature. And what was the other one with the Mandarin characters? Yeah, so we do have, what do we have? Cyrillic, we have Mandarin, we have other like Arabic, basically non-Latin language set as also one of these features. So those things should also kind of push up. But yeah, fingers crossed. Good test it.
Okay, the question was, when we use floss output as an input to rank strings, do we differentiate between the vanilla strings and the ones that were deobfuscated by floss? The answer is no, but the further answer is we are developing this with a view to, since we have control of the strings program and we have control of the rank strings program, we can add in side channel information like that. So we can say, here's the floss output, here's 2 channels for it, here's the vanilla strings, here's the exciting strings, and handle those differently. So no, but that's definitely on the roadmap. Okay, yeah, hit us outside. We got the stop sign, so we're gonna have to migrate. But yeah, we'll linger back in the corner or something for a couple minutes.